Okay. So yeah, let's treat this as I've decided to throw out the lesson. It's gone. And to anyone watching the recording in the future, if you join the Mathspace Academy, maybe you can get this kind of treatment too. There are 5 subtopics in sequences and series. So it's sequences, arithmetic series, geometric sequences, and geometric series. Can I get a vote from each of you? Pick one of these 5 subtopics and I'll do some of the tricky questions in there. Geometric series. Do you feel the same way, Drishti? Do you want to take a look at geometric series? Awesome, great. So I always like to start by looking at the lesson so we can see what we're in for. So I'm going to assume that we've already learnt about series in an arithmetic context. And I'm going to start with a so a series is when you just add up all the terms in the sequence. And there are 2 things that we need to know about geometric series. The first one is the general formula. And then there's a special case, which will come a little bit later, down the bottom, when we're talking about, oh, it's not in here. I think it will be, it's in the investigation, I see. When we have values of r less than 1 and we have a limiting series. Okay, so let's start with the basics. Geometric series is when you multiply the initial number by the same number each time. So each entry in the series, in the sequence, is going to be the initial value times some power of r, the ratio. So we're not using d, the difference, now we're talking r, the ratio. And if we wanted to add them all up like this, we get something that looks a little bit like this instead. So what happens then is essentially, I think the best way that I can describe it is black magic in terms of how we get into this formula here. What we do is we start by multiplying every single term by the ratio. The reason for this might not be so clear. So what I'm going to do is show you. I'm going to grab this annotation pen. That's what I'll do. So annotate, cool. So when you have, if you were to do something like 1 plus x squared, and you were to multiply that by 1 minus x, a cool thing happens. When you do the multiplying by 1, you get the same thing again, 1 plus x squared. That's this part multiplied by this. And then we're going to be subtracting the same thing multiplied by x, minus x squared, minus x, I should say, minus x squared minus x cubed. And the cool thing that happens is that these cancel out and these cancel out. So I'm left with 1 minus x cubed overall. So I take something that's got 3 terms in it and I multiply it by this guy, and I get something with 2 terms in it. And this is actually going to work no matter how long our thing is. So I'm going to just get rid of this annotation. Whoop. And we're going to start again with something a little bit longer. I'll tell you what, I'm just going to load up my text editor so that I can have a white page. Something bigger. Yeah, I just want a blank page. So let's take a look at. So Parminder, thanks for joining. I just thought I would mention, hey, we're not talking about financial review. At the beginning of the session, Drishti and Huon both said that they're learning about geometric series right now. And it seemed like it would be better to just teach them about something that they're learning about right now, rather than teaching them something different. So if you're doing a methods course, or if you're in New South Wales, if you're doing the advanced course, you'll come across this concept. And if that doesn't apply to you, then, well, it's still some pretty cool maths. Okay, so let's take 1 plus x squared plus x cubed plus x to the 4. We've got this long sum, and we take it and we multiply it by the same trick as before, 1 minus x. And what we're going to get is the same sort of a pattern. We get the same thing here when we multiply it by 1 plus x squared plus x cubed plus x to the 4 from the 1. But then we're going to also multiply it by the minus x, and we get minus x squared minus x cubed minus x to the 4 minus x to the 5. And all of this business all cancels out. So we started with a nice long sum. Well, it's not nice, it's bad. It's long and gross. We multiply it by 1 minus x, and we end up with something that only has 2 terms. And it's exactly this trick that we're going to use to deal with the arithmetical, with the geometric series that we want to compute. So I'm going to clear this and go back to my lesson. So you can see maybe why I'm using this trick. I've got a long addition of lots of different powers. And I'm going to take this sequence and multiply it all by r. And then I'll be able to subtract them. So let's do that over on this page. Get my annotations out again. So I've got Sn, fail. Annotation not on. Here we go. So I've got Sn equals A plus the initial value plus the initial value times the ratio plus the initial value times the ratio to the power 2 plus all the way through to plus the initial value times the ratio to the n minus 1. Now it's just going to get rid of those because that's a gross n. Try that one again. N minus 1. It's always tricky to keep track of your subscripts and superscripts and powers and whatever in this area, but just there are n terms here. Now, if I multiply all of this by r, I'm going to shift it over 1. So I'm actually going to write this as, it should just be right underneath AR, but I'm going to rewrite it over here. AR plus AR squared plus, and then I'm going to get, Coming from the AR to the n minus 2 over there, I'm going to get AR to the n minus 1. And then this one is going to give me my last term, AR to the n. And then I'm going to do the same subtracting trick that I showed you just before. If I subtract one from the other, I'll end up with what I'm looking for. So let me just check that I'm subtracting it. Yes, no, I did think I was subtracting it the right way around. So if I subtract the bottom row from the top row, what do I get? Sn minus Rsn equals A minus AR to the n. And we don't have any more dots left. There's a particular word for this in mathematics, and if you go and study mathematics at university, you'll learn that this is called a telescoping sum. A little bit of terminology just in case. So now we just need to, because Sn is the thing that we've wanted to figure out this whole time, this is when we find that magical factor of 1 minus r. It was 1 minus x in the thing that I was showing off earlier. 1 minus r Sn is a minus a, and I'll tell you what, let's factorize this side as well. I've got a's here, a 1 minus r to the n. And then finally, I end up with Sn equals a 1 minus r to the n over 1 minus r. Now this is cool because what do we need in order to make a geometric sequence work? We need an initial value, that's our a. We need a ratio, r. And we need, if we're looking for a series, it's just the nth term in the series, an n. So if you know each of those things, you can plug it in and find out what the value of that series is at that particular value. Are you talking about this one here? Is this one a plus? The reason why it's not a plus is because I'm subtracting this. That's why it was AR minus AR, AR squared minus AR squared, and so on. So this one's positive, but even though it's plus on this line, I'm subtracting this one here from that one. Okay, cool. So Sn minus Rsn, and so on. So this is our formula, and I'm sure it'll appear on your formula sheet. And so it's as I said, it's a bit of black magic. It's just one of those times when mathematics works out just right, and it's kind of spooky and awesome, and that's why we love mathematics. So I'm going to clear this and get out of the annotation mode. And so we can see here that this is the formula. Now, I will note, as the lesson says, that you can flip the signs around, multiplying both the top and the bottom by -1 if you want to, but really it just gives you another formula to memorize. This is the only one that you're going to need. There are some alternate formulations. If we come across those, we'll deal with those as we go. So let's see the kinds of questions that we might be asked in the realm of geometric series. I'm just going to open up questions in a new tab. I'm going to try some of these out. And I will remind you that if you do anything in the textbook arena, you're not going to get mastery for it. Okay, let's take a look. Let's do this one. Yeah, this one looks good. Okay. So this is definitely the very beginning one. Okay, we've got a series 2 plus 6 plus 18 and ... We want to find the sum of the first 10 terms. In order to use our formula, and we always want to write our formula down, so Sn, oh, whoops, sorry. I'll try that again down here. Sn equals A 1 minus R to the n over 1 minus R. If we want to do that, we have to figure out what all these numbers are. The one that's easiest to find in this question is n. We've been given the sum of the first 10 terms. So I'm going to put that over here in a different color because we know this one. N equals 10. A is the first term in the sequence. Now it's not presented as a sequence, it's presented as a series. So it's got pluses. But the sequence would be what you get if you put commas instead of pluses. So I can tell just by looking at it that the first term, A, is 2. And then, finally, what number is multiplied to go from 1 to the next? Well, to get from 2 to 6 and to get from 6 to 18, because we're looking at a geometric sequence or series, it's a multiplier. So we add 4 and then add 12, so it's not arithmetic. Instead, we are multiplying by 3 each time. R equals 3. Okay, we got it. In it goes, and then we just turn the handle. So S10, again, new color, I like using colors. S10 equals 2 times 1 minus R is 3 to the power 10 over 1 minus 3. So now that we're in an example, you can see why we might want to write it the other way around, because I know that this value, 1 minus 3 to the power 10, is going to be negative. And 1 minus 3 is also going to be negative. So I could write it differently by putting it as a different formulation. 2 times. If I multiply the top and bottom by minus 1, then I get 3 to the 10 minus 1 over 3 minus 1 instead. But this is entirely optional. Realistically speaking, once you get these numbers, you can just throw them in the calculator. There is some nice cancellation we can do here though, because 3 minus 1 is 2, so they cancel. So it's just 1 less than the 10th power of 3. Okay, let's open up old mate Google. 3 to the 10 minus 1. This one. Copy and paste. Awesome. Okay, so that's one of the more basic versions. You've seen the formula in action now. I'm going to take a look for one that's a little bit harder. But if you have a particular question that you can see in here that you'd like me to do, please let me know in the chat and I will do that one. I'll give you a few moments in case you have any recommendations. But if you don't have any recommendations, I'll find a nice tricky one. We might talk about the sigma notation. I think I'd prefer to find maybe one of these application questions. Someone said, yes, please. Was that for the sigma notation? Okay. Let's do this one. Sigma notation is, what's a good way to describe it? Sigma notation is really powerful and really awesome, but it can be a little bit confusing. So what I'm going to do is I'm going to do these two questions, this one and then this one. Okay, let's do it. Try a question. Sigma is a big Greek S and standing for sum. And it has three important components before we even leave the symbol. We have something that indicates the index some number indicating the value where we start, the minimum value, and then up the top we have the max. So what does this mean? What we're going to do is we're going to figure out what the index is, and we're going to replace that index with the minimum value, then the minimum value plus 1, then the minimum value plus 2, and so on all the way until you get to the maximum. So that's the general form of sigma notation. What have we got in this question? I'm going to change colors. We have, I'm going to draw it a little bit smaller this time. Sum j equals 1 and 5. This is telling us that in what follows, in this bit here, j is the index. And then we just write down what's going on here. 64 times 1/2 to the j. So the index will almost always appear in the expression. So as I said, we take the index and we replace it with the minimum value. We just rewrite the whole thing, 64, 1/2, and we replace the index with the minimum value to the power 1. Plus, we then increase by 1 and do the same thing again. We rewrite the entire expression, 64, 1/2, but remember that we increase the index by 1, so we write the 2 instead. We increase the index again, plus 64 times 1/2 cubed. Now, in practice, we're not actually going to write this all out every time. We're just going to write, we're going to use sigma notation really in a powerful way. I'm just explaining how it works. I don't think that this is useful working for you to do in your exam, but it's very useful working for you to do when you're first learning about sigma notation. Plus 64 times 1/2 to the power 4, and I keep increasing by 1, 64 to the power 1/2 to the power 5. Now that my index has reached the maximum value, I stop. So just to recap, this is telling me that this whole blob, all of this, represents the sum that you get, sigma sum, where if you take the expression of this form and start at j equals 1 and add up by 1 each time until you get to 5, then these two things are the same. But it takes a lot less time to write what I put a box around than it does to write everything out all one by one. So now we need to actually find what this thing is. In order to find this thing, we have to recognize first that it's a geometric series. We do that by noticing that what changes between each of these values is it gets multiplied by a half. This is 64 multiplied by a half once. This is 64 multiplied by a half twice. 64 multiplied by a half 3 times. Each time we're adding on a multiplied by half. So what's the initial term? A equals. Now this is where we can easily trip ourselves up. You might think that it's 64, but it's not. The first term is the first term as it appears in the series. So the whole thing, 64 times a half, is the first thing here. So A is actually 32. Sometimes you will see sigma notation where the bottom number is 0. If this bottom number was 0, then the first term would be 64 times a half to the power 0, and 64 would be the first term. But whatever comes out first, whatever you get from the minimum index is going to be our first term. Then we say, what's our R? R is the value we multiply to get from one term in the sequence to the next, and that's a half. And N, the number of terms in the sequence. In this case, that's 5. Okay. So A, R, and N, we found them all. We're ready to go with our formula that we used just before. Okay. I'm going to get out of this and I'm just going to do it straight into Mathspace. So the formula is that we take the initial term, 32A, times 1 minus R, which is a half. And when it's in the numerator, that needs to go to the power of n, which is 5. So I've put in A times 1 minus R to the power n, and then we divide all of this by 1 minus R. Looking good. So let's simplify this a little bit. 2 to the power 5, 2, 4, 8, 16, 32. Okay, and 1 minus 1 on 32 is 31 on 32. If I have 32 32s and I take away 1 32, then I'm left with 31 32s. Yeah, no, that's right. All right. Cool. Now 32 times 31 over 32 is just 31. Cool, cool. More simplification, that's what we like to see. And then dividing by a half is the same as multiplying by 2. 62. Haha, got there first. Nice job. Answer live, is it 62? Yes, it is. So is the counterintuitive part, so I assume that, I don't know, maybe you can see that, maybe you can't. It seems counterintuitive because it's like we start at 64 and how do we only end up at 62? Yeah, okay. So the first thing to notice is that we don't actually start at 62. We start, oh, sorry, we don't start at 64, we start at 32. 32 is our first term and we add up as we go. And so we start at 32 and then we add a bit and a bit and a bit. yeah, we do get incrementally closer. So we will potentially eventually get to 64, but only after an infinite amount of time. And I'm going to, I was going to save this till the end. I might as well jump in right now. So I'm going to, yeah, let's just have another one of these. Just open this one up again. So ignore the question that comes up. We're not answering that question right now. Instead, what we're going to do is we're going to think about this sum. 1 plus a half plus a quarter plus 1 on 8 plus 1 on 16 plus ... Now, just as an exercise, what we're going to do is we're going to rewrite this in sigma notation, just as an exercise in learning about sigma notation. Then we'll get to the bigger conclusion elsewhere. All right. So if I want to write this in sigma notation, before I go anywhere, remember that sigma always has a minimum and a maximum. So we need to figure out what we're going to sum up to. The one thing we can observe about this particular series is that it's 1 over a power of 2. So I'm going to write that as 1 over 2 to the power n. So I can see that this is when n is 1, this is when n is 2, this is when n is 3, this is when n is 4, and so on up to some value. And this general form for the terms in the series gives us a clue of what we need to put here when we rewrite it in sigma notation. Now, what's our starting point? What power of 2 do we have at the beginning? It's actually to the power 0. So 0 is our starting point and n is our finishing point. The thing that we're looking at is 1 over 2 to some power. And what we need to put here is the counting index. In the last problem, it was j. We can see j lurking over there. Let's use j. J equals 0, 2 to the power j. Let's just check that we've got this right. It can be a little tricky with sigma notation because now we've got 2 different pronumerals, 2 different letters. But j is just the counter. What we do is we put 0 where the j is, and we get 1 over 2 to the power 0, which is just 1, and that's our first term. Tick. Then we increment, we add 1 to j and put it where j is, 1 over 2 to the power 1. And that's this one. Tick. Then we go to 2. 1 over 2 squared is 1 over 4, and we get that one. And then we keep going, adding up by 1 each time until we get to n, which is our stopping point. Okay. So this big sum can be represented in sigma notation like this, and maybe you can see why mathematicians love sigma notation so much. Instead of writing something like this and it's got ... dots, it looks all ugly and stuff, here I've just got a nice little expression that expresses everything I need to know about the sum. If you learn sigma notation properly, you will never have to write ... ever again, which is cool. But let's switch over now and let's not do the sigma notation bit anymore. So I'm just going to get rid of this. And instead, we're going to use the geometric series formula to find out what this sum is going to be in terms of n. All right. Sn, and this time I'm going to leave the n. This is the sum in terms of n, because we want this n to be whatever we like. What's the first term? It's 1. Awesome. Then we do 1 minus the ratio, and we can tell that the ratio here is a half. 1 over 2 to the power n. And all of that is divided by 1 minus the ratio, which is a half. 1 minus a half is a half, and dividing by a half is the same as multiplying by 2. So to simplify all of this biz, all of the denominator, I can just rewrite this as 2 times 1 minus 1 over 2 to the power n. That was just me cleaning up the denominator there. Okay, so now when I expand this bracket here, what do I get? I get 2 minus 2 times 1 over 2 to the n. And this is telling us something really interesting. A guy named Leonhard Euler, who I'm sure you'll hear more and more about as you advanced in your mathematical career, figured something out. And that's that what happens if n is big, and like we're talking really, really, really big. Well, if n is really, really big, then 2 to the n is way bigger than that. But a half to the power n, that's the same as 1 over 2 to the n. If it's 1 over a really big number, that's the same as it being a really, really small number. And so the conclusion is that as n gets really, really big, this blob, all of it, goes to 0. Let's think about what that means. If I start with a 1, and then I add a half, add a quarter, add an eighth, add a 16th, add a 32nd, add a 64th, and keep on adding, I will get closer and closer to 2, but never quite get there. I'll definitely never get more than 2, because it's 2 minus something. But I'll get closer and closer each time. And that's the same phenomenon that we were looking at in this question, where we started at 32, and then as we added more and more terms, we're getting closer and closer to 64, but never quite getting there. Just saw something come up in the Q&A. Yes, the word is convergent. There's another famous series, since I'm already going off on a tangent. There's this one, it's called the Harmonic Series. 1 plus a half plus a third plus a quarter plus and so on. Now this one is not like this one. It's not a geometric series because there's no number that multiplies from 1 to a half that's the same as going from a half to a third and a third to a quarter. There's no common ratio. So this is not geometric. And as this continues, this always continues to get bigger. It takes a long time because eventually you are adding 1,000th, 1,001th, 1,002th, and you're only adding little bits, but you always, always, always keep getting bigger. So this is not the same as what we're talking about here with these series. Okay, I've got a few minutes left. I'm going to have another look and see if I can find anything else that looks interesting. Okay, well, those ones are all a bit long. Okay, let's take a look at a shorter one that's down the bottom here. Oh, there was one to rewrite it in this one's a tricky one. Yeah, let's do this one. Okay. We've got to write this in summation form. Okay. So remember what we need to do. Well, the first one is easy. It's going to have a big sigma in it. So we might as well start with that. What we need to do is we need to think about what the general term is here. So let's notice a few things about it. We've got alternating signs. It goes minus, plus, and so on. So that's going to be a little bit tricky. A good way to do minus, plus is a power of -1. I'm going to start from the beginning. Notice that they've given us the things k equals 1 and n. So I'm going to write that in, k equals 1 to n. And so how do I get, when k equals 1, I want the thing to be positive, but when k equals 2, I want it to be negative. I'm actually going to do that using a nice trick, which looks like this. This is only the sign part, but let's think about why this works. If you do -1 to a power, then what's going to happen is that when the power is odd, then we get a negative. And when the power is even, we get a positive. So if we start at k equals 1, I put a 1 where the k is, and I get 1 plus 1 is 2. And -1 squared is positive. Then I go to k equals 2, the next one up. I put 2 where the k is, -1 to the 2 plus 1 is -1 cubed, and -1 cubed is negative. So -1 cubed gives me the minus, and that will give me my minus for my next term along. Then it will go back to plus, minus, and so on. This is a very handy little gadget, and it comes up a lot in sequences and series, especially whenever you're using sigma notation. -1 to the power. The only other thing we need to do, now that we've accounted for the sign, is let's ignore the sign and see about how we're going to write this. But I think we already know how we're going to do this one. It's going to be 1/2 to some power. What we want though, so we've already figured out that when k is 1, we're going to get a positive. But when k is 1, we also want to make sure that this thing on the bottom is 2 to the power 0, not 1. So in this case, we're actually going to do k minus 1. And once again, let's just check why this works. When k is 1, k goes up here as a 1. 1 minus 1 is a 0. 2 to the power 0 is a 1. And all over, we just get a big 1. Then as k goes up to 2, I put the 2 where the k is. 2 minus 1 is a 1. So the power becomes a 1. And overall, I get a half. And then it ticks up again. 1, half, quarter, 8, so on. The very last thing we need to do is figure out what the value of n is. The one fact that I do know is that 2 to the power 10 is 1024. So we need to count k up until this power becomes 10. So you might think that the answer is 10 up here. It's not quite. Because if we stopped at 10, then when we take 10 and replace it where the k is, we get 10 minus 1 is 9. We fall 1 short of the final term in the series. So instead, we actually need to go all the way up to 11. That's how I know when I can stop, because I put k as 11 in there. I get 11 minus 1 is 10, and I get 1 over 2 to the 10, which is this final one here. Okay, well, I hope you guys appreciated the crazy last minute throw everything out diversion. The join code I gave you, I don't know how long that will be valid. If you don't currently have access to Mathspace, I highly encourage you to talk to your parents and get them to organize a homeschool package. It's $30 and you get all of Mathspace, and Mathspace is pretty cool. But thanks guys, and I will see you next week.